I've been checking on YouTube. You guys have not been, if you missed a class, you have not been following up to watch them on YouTube. So I was even discouraged. I was even thinking maybe I should not be posting them on YouTube because you guys are not watching. You are not watching them.
No, sir. You should be recording.
But I record, you guys don't watch. What's the point of recording?
Sir, we had no bundles, sir. We'll watch it.
Yes, yes.
So anyway, I'll see. But that's what we are saying. We are saying that perfectly in elastic collision, momentum and kinetic energy has to be conserved. So that's what I'm saying. Elastic collision, we have to make sure that kinetic energy is also conserved. But in elastic collision, only momentum is conserved, kinetic energy is not conserved. Inelastic. Perfectly inelastic is also similar to inelastic, but here in perfectly inelastic, after collision, the two bodies stick together. Even though kinetic energy is not conserved, but the two bodies stick together after collision. And are we together thus far?
No, sir. Me, I'm now confused.
Okay, Chipo?
Yes, sir. Here you're saying on elastic kinetic energy is conserved. Does it mean one object is at rest? Because you've only written one kinetic energy, one initial kinetic energy here.
Okay, could you speak a little bit louder? I was not getting.
I mean, on elastic collision, you say kinetic energy is conserved. But here I'm only seeing one initial form of kinetic energy. Does it mean one object is at rest here?
Yes.
On elastic.
That is what I said.
Yes. So, but what's the difference between elastic and inelastic again?
Okay. So where we are coming from is we are coming from this diagram. We are coming from this diagram. What we are talking about is with respect to this diagram. One object is at rest, another object is moving. So when an object is moving and another object is at rest, what we see is that if the collision is elastic, we have to make sure that momentum is conserved. We have already shown how momentum can be conserved in the x-axis and in the y-axis. And then we also are showing how kinetic energy is conserved. So kinetic energy, we have only shown for mass 1 because the other object is at rest. The other object is at rest. It will not have kinetic energy. But at the end of the day, we must make sure that when we calculate the kinetic energy of what we have in the initial, I've even shown here initial I. What we have shown here initial, when we calculate it, if it is equal to what we have here in the final, half mv squared for mass 1 and half mv squared for mass 2. If what we have here is equal to what we have on the other side, then we call this collision elastic collision, elastic, because both kinetic energy and momentum is conserved. Is that clear on elastic? You have gotten it?
Yes. Now inelastic, what does it imply?
Inelastic is the opposite of this, meaning kinetic energy is not conserved. If you calculate this, what we have in the initial stage, if you calculate the kinetic energy here and you find that it's not equal to what we have in the final, then you know that it is inelastic. If it is not equal, all right? If instead of...
But the questions are the same.
Yes. If you find that this is not the same, if this is not equal to that, then it is inelastic collision. But momentum is conserved just like the way we described it. Even in inelastic collision, momentum in the initial stage or momentum in the x-axis has to be conserved and momentum in the y-axis has to be conserved. Only kinetic energy will not be conserved on inelastic collision, but the equations are the same. But when you discover that when you are determining and calculating your kinetic energy, you discover that what you have in the initial is not equal to what you have in the final, then you know that it is inelastic collision.
Okay, sir.
You get it?
Yes.
Are we following, friends? Can we move on now?
Yes, sir.
Okay.
Of course.
So, I also talked about the case of impulse. Chipo talked about what if there's a force applied to it. So we are saying that another important term to define is impulse. Impulse in physics refers to the change in momentum. Now, when momentum changes, here we are saying momentum is conserved, meaning it doesn't change. What you have in the initial has to be equal to what is in the final. But if what you have in the initial, if you find that what you have in the final minus what you have in the initial, there is some value. That value, we call it impulse. So if you change your momentum, meaning you have applied an external force, if there's no external force applied, the momentum will be conserved. So we are saying that if, for example, we have one mass, if we change its velocity, that change in velocity multiplied by the mass will give us the impulse. And this impulse is when a force applies to an object at a given time. So when a force applies to an object at a given time, it will accelerate, it will change the velocity. Change in velocity means acceleration. So if you apply a force at a given time, velocity will change, and then you will have what we are calling impulse. And this force can be calculated by change in momentum over time. Change in momentum over time will give us, will give us the force. Change in momentum over time will give us the force. Are we okay now about how a force comes in to change momentum?
Yes.
Sorry, sir, kindly repeat.
Okay. So, all the way we have been talking about momentum being conserved. Here we talked about that what we have in the final has to be equal to what we have in the, what we have in the initial has to be equal to what we have in the final. Momentum is conserved. Even kinetic energy for elastic collision is conserved. But when we talk about impulse, impulse is now the situation where momentum is no longer conserved. Momentum is changed. When we change momentum, mv final minus mv initial, that change in momentum, we call it impulse. And it is just simply the change in velocity of an object multiplied by its mass. When a velocity changes, multiplied by its mass, it makes, it causes, we calculate that as impulse. And then we are saying that this impulse is the same as when a force acts upon a system at a given, for some interval of time. So when a force acts on a mass, for example, if I come and start pushing Eunice, I start pushing her with some force. If she was stopping, if she was seated, I start pushing her with a constant force, I'll change her momentum if I apply a force for a given time. And that is what we call impulse. So this is where now a force comes in. And we are saying that force can be calculated by looking at the change in momentum in a given time. Change in momentum over time gives us that force. Are you okay now?
Yes.
Okay, just a short period, just a quick one. Let me put some water in the pot cooking. Okay, so we discover that someone can be both a tutor and a cook. That is the goodness of being at home. So we are back. Now, let's quickly now look at some solving. We have looked at so much on just what's this? We have looked so much at just theory. Let's look at some solving. Are we together?
Yes.
Yeah.
Awesome, awesome, awesome. So let us have Florence to read for us the question she can see on the board there. Question 1, Florence.
It reads, car 1 was sitting at rest when it was hit from the rear by car 2 of identical mass. Both cars had their brakes on and they skidded together 6 meters in the original direction of motion. If the stopping force is, I don't know whether it's negative 0.7 times combined weight of the car, that is combined weight of the cars, comma, that is mu is equal to 0.7. Find the approximate speed of car 2 just before the collision took place.
Okay, so what you see here is they are saying if the stopping force is 0.7 times combined weight of the car, this 0.7 is the mu. You know that if you have the weight or the normal force multiplied by the mu, you get your friction force. So that is what they mean by the stopping force and all that. And good reading, good reading. Like I always try to emphasize, I'm sure you guys have, maybe some of you guys have attempted this question or you saw this question. In fact, I solved it again with the rest of the group, NS PCM group. But I would like us to also go through it again and see what we can learn from it. So, and what I always emphasize is that when you read a question, ask yourself, have I really understood the question? So, if I ask you, Florence, when you were reading the question, what do you think the question is asking for?
I haven't understood the question that much.
Read it again and try slowly but surely. Read it again and slowly but surely. You are reading?
Yes.
I thought we were supposed to be hearing someone reading.
Oh, I read.
Yes, yes.
Yes, yes. Car 1 was sitting at rest when it was hit from the rear by car 2 of identical mass.
You wait there. You have read this word as rear. So if there's a word that you don't understand, it becomes a challenge there. It's not rare, it is clear. Meaning from behind. If it is hit from behind. So you have to make sure you understand that word here. Then you continue on. So car 1 is at rest, another car hits it from behind.
Okay.
Continue.
Both cars had their brakes on and they skidded together 6 meters in the original direction of the motion. If the stopping force is 0.7 times combined weight of the cars, that is combined weight of the cars, comma. So the 0.7 is mu 0.7. Then we asked to find the approximate speed of car 2 just before the collision took place.
Awesome. Awesome. So now you understand what the question is saying?
Yeah.
Yeah, okay. Okay, so the question is talking about, I've even drawn here, this is, let's call this one car 2, and this is car 1. Car 1 is stop, is just there. Then car 2 comes and hits into car 1. But then when they hit into each other, both of them apply brakes. But then they discover that after the point of impact, they skid some other distance of 6 meters. Now, can we manage to find this, the velocity at which car 1 was moving, so that after it hit car 2, or the velocity of this, okay, you can pick whichever one to be your car 1 or whichever one to be car 2, as long as you do the calculations with consistency. So if we can find the, can we manage to find the velocity of this one, car 2, so that once it hits into car 1, they're able to skid like that with the coefficient of friction given as this one? Is it possible for us to find velocity of car 2? What equations are we going to implement? Let's see now how we're going to look at it. So, in fact, for me, when I was solving, I considered the car that was moving to be velocity 2, or to be mass 2. So we have even been told that the two cars are of identical mass. Where are we? Identical mass. So once they have told us that the two cars are in identical mass, we know that mass 1 and mass 2 are equal. So velocity, what velocity have we been told to find? We've been told to say, find the approximate speed of car 2. Car 2. We already know that car 1 is at rest, meaning it is its velocity. We have been told that car 1 is at rest, so meaning its velocity is 0. But car 2, we don't know its velocity. So we know that car 1 is 0. Car 2 is, we don't know its velocity. Now, we know that car 1 and car 2, finally, they stick together. How do we know that? Because they told us that both cars have their brakes on and they skidded together. So when they are skidding together, meaning their velocity becomes the same. So finally, velocity 1 and velocity 2 becomes the same. And if velocity 1 and velocity 2 becomes the same, what type of collision is that? Eunice, could you help us? What type of collision is that if velocity 1 and velocity 2 in the final stage become equal? What type of?
Perfectly inelastic.
Good. Excellent. Yeah. So this is perfectly inelastic. So The distance traveled after impact is 6 meters. Now we have to make sure that we write the equations of momentum, because even in perfectly inelastic, momentum is conserved. So I say momentum 1 initial, momentum 2 initial has to be equal to momentum 1 final and momentum 2 initial. Now, since the masses are the same, we can cancel out this m, all right, and have that mass 1 we're told was at rest, mass 2 had a velocity, but at the end of the day, the two velocities, the two masses go with the same velocity. No wonder we are saying we're even putting 2v, because this is velocity for 1 and velocity 2 is the same. So if velocity for 1 and velocity 2 is the same, if we add them, they'll become 2v final. And let's see now. This is what we're saying in question 1. Question 1. Now, let's see how we can deal with equation.
Sir, wait.
Okay.
Kindly explain from here what is MV1 plus MV2 on the equation until here you've reached.
Okay. There's another one also with a question. That was done.
Yeah, I have a question, sir. Now, sir, on the type of collision, sir, what if someone says it's a glancing collision?
I even said it. I think I explained it. I explained that glancing collision is a collision, for example, in 2D. In 2D here, when an object just hits, it's not a head-on collision. It's just a glancing where someone just it just glances you, such that one object deflects in one direction and another object deflects in another direction. So this, what you see here, is an example of glancing collision, where it's not a head-on collision. One object gets to deflect in another direction and another object deflect in the other direction. So that, my friend, is what is known as glancing collision.
All right, thank you.
So let's quickly go and finish up what we are doing so that other people can also finish up. So this is what we have here. Eunice, you were saying you didn't understand how we did what?
I was saying kindly repeat on the explanation from the equation here what is distance traveled after the impact from here to equation 1.
So this is data. Under data is because this is the information that we're given in the question. Now, this is just the equation of momentum. All right. Equation of momentum tells us that momentum 1 initial plus momentum 2 initial has to be equal to momentum 1 final plus momentum 2 final.
Yes.
And then remember we said that mass 1 and mass 2 are the same, because they told us that the two cars are identical. So if mass 1 and mass 2, we don't even need to write it as mass 1, we just write it as m, because mass 1 and mass 2 are the same. So now we can cancel out these masses like that, like that. And then we also know that the momentum for car 1, we are told that velocity is 0. So initial momentum for car 1 is 0. Now, since we have cancelled out here, we only remain with V2. Now, since V1, we are saying V1 and V2 are the same. When we add them, if you and if Eunice and Chipo have the same masses, have the same grades, if we add them, when they be 2 times the velocity of either of them. So no wonder we have 2 VF, because velocity here and velocity there is the same. That's what we are saying here. So we have 2 VF. Is that okay?
Yes.
This is equation 1. And then equation 2, since we have been given the coefficient of friction, remember, we were given the coefficient of friction, this one. Let us also try and make another equation. So it can help us to calculate the what's this? Friction force. And the friction force will help us also determine the deceleration. All right, if we know the friction force, we can know the deceleration that caused it to stop in 6 meters. So, because both tires were put to brakes and then they started skidding on the tarmac, so we expect that there was some friction force on the tarmac. And the friction force is just simply normal times mu. All right. Now, normal times mu, normal is equals just to mg. Now, since we have two masses, all right, we can write them as 2 mg. So our normal will be 2 m. The masses are going to cancel out as well, as we see. But what we are saying is that the friction force is normal times mu, which is mg. Now, because we have two masses, we are writing 2 mg. Now, mass, or should I say friction force, force always produces acceleration. Force always produces acceleration. So this is the friction force. This is friction force. And this is mass times acceleration. The reason why we're putting 2 is because there are two masses with the same acceleration. All right. We have determined that the friction force will be normal times mu. Now the normal is 2 mg because we're dealing with two masses, and then this eventually should be able to produce acceleration, and 2 because there are two masses. So this and that will cancel out. So we'll end up having g times mu is equals to a. So g times mu is equals to a, and actually it gives us 6.8 meters per second squared. Now, since we know this acceleration A is deceleration. Why are we saying deceleration? Because it caused it to stop. They skidded, both cars skidded in the original direction of the motion. If the stopping force, so we are talking about a stopping force, and if we are talking about stopping, then we are talking about negative acceleration. So the acceleration that we have found is a deceleration, and it's negative acceleration. Are we following? Are we following, friends?
Yes, sir.
Yes, let us always be saying yes or no so that I know that you guys are there. Are we following?
Yes, sir.
Okay. So we have found our acceleration. So how do you solve physics problem? Physics problem is just a matter of saying, okay, I have this. How do I get from a point where I have this to a point where I have that? So physics is about asking yourself, I've been given the coefficient of friction. What do I need? What can I do with it? So since this object or this system is eventually going to stop, I must find out the rate at which it was stopping. Meaning I must find out the deceleration. How can I find the deceleration? And then if you find the deceleration, how can this deceleration help me? Because at the end of the day, what are you looking for? Never lose focus of what you're looking for. What you're looking for is the approximate speed of car 2 just before the collision. So before the collision, what was the speed of car 2? Now, how can I find this? That's why we are going through all this process to see, okay, if I can find the deceleration, maybe I can find out how much the velocity of car 2 is. Remember in the equation, we have this V2. initial is equals to 2v final. So if I can find maybe v final or something like that, I can find velocity of car1 initial before the collision, because that is what the question is asking for. So what we are going through in doing all this is just to make sure we go back to where we are coming from. So it's a matter you do this, you do that, so that you get what you are looking for. So we have determined the friction force to be like that. We have found even the acceleration. Now, what can we do? If we have the acceleration and we have the distance, can it help us to find the velocity, especially at least if we can find the velocity after impact? Because after impact is when they applied the brakes to stop. After they collided, they applied the brakes. And we have seen that when they applied the brakes, it produced this deceleration. When they applied the brakes, it produced a deceleration. So can we help? Can we find something here? So using the acceleration that we have found, again, Zoom is saying that time is running out. So quickly you go back again to the link so that we finish up this question. I think when we finish up this question, then I think we'll be done for the day. So that we get to do other things. Also, we'll see how time will go. So what we are saying is that from there we can calculate the velocity just after impact. If we can find the velocity just after impact, it will give us a window of finding the velocity before impact. And then using the deceleration that we have found, we can use this equation. V squared is equals to U squared plus 2GS. Now we know that if we use this equation, since the two cars will come to rest,